Assalamualaikum and good morning to our lecture. My name is Muhammad Dizarfan and my partner name is Muhammad Sahari bin Yasin. Today we will be presenting our mini project titled Gas Sensor System for Confined Space. Without further delay, let's begin with the introduction. This project focuses on improving the reliability of gas detection system used in confined industrial space such as storage tank, pipelines, and sewers. These environments are considered hazardous because poor ventilation can cause toxic or explosive gases to accumulate or creating serious risk to workers. One major challenge is the use of metal oxide semiconductor or MOS gas sensor. Although these sensors are low cost and widely used, their performance is affected by environmental conditions such as temperature and humidity. Change in this condition cause sensor baseline drift, meaning the sensor normal resistance change even when no gas is present. This drift can lead to false alarm or even failure to detect dangerous gases, reducing the reliability of industrial safety system. To investigate this issue, the researcher used a dataset containing 4,769 sensor measurement collected at University Malaysia Perlis or UNIMAP under tropical climate condition. The system used three different gas sensors, namely TGS 2442, MQ4 and MQ136 to analyze how environmental change influence sensor behavior and improve gas detection accuracy. There are three major problems addressed in this project. The first problem is environmental susceptibility. Low-cost MOS gas sensors are highly sensitive to change in temperature and humidity. This environmental change affect the chemical reaction on the sensor surface, causing inaccurate reading. The second problem is the risk of false positive alarm. When the sensor drift occurs, the system may trigger alarm even though there is no actual gas leak. This can interrupt industrial operation, increase costs, and cause workers to ignore future alarm because of alarm fatigue. The third problem is the algorithmic deficit. Many existing gas monitoring systems do not have intelligent algorithm capable of separating environmental noise from actual gas signal in real time. Therefore, there is a need for a smarter, data-driven solution that can improve the accuracy and reliability of gas detection system. This project has three main objectives. The first objective is to identify the behavior of the gas sensor. We conducted controller testing using three different gas sensors, namely TGS 2442, MQ4, and MQ136, inside a sealed chamber. The sensor were tested under tropical environmental conditions, where the temperature ranged from 16 degrees Celsius to 30 degrees Celsius, while the humidity ranged from 45% to 75%. During the experiment, we continuously monitored the sensor to observe how change in temperature and humidity affected their resting resistance, also known as a sensor drift. The second objective is to analyze the collected data. First, we use percent correlation analysis to determine the relationship between environmental condition and the sensor reading. Next, we apply ordinary least square or OLS linear regression to evaluate whether a simple mathematical model could composite for sensor drift. Finally, we measured the variance to determine exactly how much sensor error was caused by change in temperature and humidity. The third objective is to predict gas hazard and improve monitoring using artificial intelligence. We trained a decision tree machine learning model to distinguish between actual gas hazard and environmental noise. The aim is to reduce false alarm while maintaining high detection accuracy to improve worker safety. Finally, the monitoring results are displayed on a Teamsboard dashboard where user can view real-time, color-coded risk level, allowing faster and easier decision making.
We're moving to the system specification. There is a flowchart which is for the data collection, which is start from data collection and ending with the reporting. So the first one is the data acquisition layer. Data acquisition layer is a gathering of raw environmental variable, which is the temperature, humidity, gas sensor resistance values into the spreadsheet. Second one is the data processing integration layer. Clean and tag data, which is remove null values, align timestamp, corrects timing offsets, and label distinct data segment. It also analyze data and extract system pattern using three distinct analytical vectors, which is the first one is descriptive result vector, correlation data vector, and a regression data vector. And also is consolidate analysis that gather the output vector into a single structured data set and use a Python pipeline to package the consolidated data into JSON telemetry payloads, and also is push telemetry to Teamsboard and upload the formatted JSON payloads to the Teamsboard cloud gateway using an API request. The third one is visualization and deployment layer. We design Teamsboard visual dashboard, which is create visual layout containing the master table, markdown info card, and max temperature card. Also that we have the testing alarm validation loop, which is verify if the cell styling JavaScript threshold triggers color correctly based on sensor resistance, which is red for resistance drop below 5000 ohm, or warning for orange, which is resistance sits between 5000 ohm and 15000 ohm, and safe for green, which is resistance exceeds 50000 ohm, which is the clean A baseline. And also decision if trigger fail, the system looks back to design phase. If they pass, which is yes, it deploy. And also it publishes the fully validated interactive dashboard for us for user monitoring. And last but not least is the analytical reporting, which is filter historical timelines via the dashboard to export structural compliance and system safety report. Now we move to the graph. In this project, we managed to bring out 5 graphs. So the first one, which is the ambient temperature and relative humidity profile over time, which is on the top left. It displays a dual line chart tracking environment fluctuation over the return timeline, which is the horizontal axis. The data trend is actually a temperature that is blue line that begins around 29 degrees Celsius and then dips slightly below 25 degrees Celsius near point 826, and then steadily climb to peak over 35 degrees Celsius near point 3796 below leveling off. Humidity, which is the red line, behaves inversely. It spiked initially up to nearly 59%, exhibit a sustained dip down to 33% during the mid phase, and climb sharply to hold at the high level toward the end. This is the significant that established the changing atmospheric baseline of the testing environment. For the second graph, the correlation between ambient temperature and RSMQ4 sensor register, which is on the top right. It displays a scattered trend plot mapping temperature, which is the horizontal axis, directly against the resistance of the MQ4 sensor, which is the vertical axis. It shows a nonlinear loop behavior with an R-square value of 0.2896. The resistance primarily clustered between 3000 ohm and 5000 ohm with a large upward peak towards 7500 ohm, occurring right around the 30 degrees Celsius marks before dropping back as temperature pushed past 33 degrees Celsius. The third graph is a multi-sensor gas resistance response on a logarithm scale over time on the bottom left. It displays a time series line chart evaluating all three gaseous sensors simultaneously using a logarithmic vertical axis, which is 1 to 1 million ohm. The RS TGS2442, which is the sensor for red line, operates significantly higher than the others, maintaining a flat baseline above 100,000 ohm. The RS MQ4, which is the green line, and the RS MQ36, which is the purple line, track much lower, grouping tightly together in 2000 ohm until 7000 ohm. For the fourth graph, which is the comparison of MQ series gas sensor resistance and environmental variable over time. It displays a multi-axis overlay chart directly comparing the low resistor profile of the MQ sensor against the environmental parameter. The shaded blue area tracks the raw fluctuation of the MQ series sensor over time. The green and brown line overlay highlight how drop in gas sensor resistance closely aligned with specific shift in ambient temperature and humidity level. And last but not least, the fifth graph, which is the relative resistance contribution of MQ and TGS gas sensor over time, which is on the bottom right. It displays a 100% stacked array chart highlighting the proportional share of total resistance contributed by each sensor, zoomed into 92% to 100% bracket. The RS TGS2442, which is the blue area, dominates the proportional share, consistently claiming 95% to 96% of the overall resistance load. RSMQ4, which is the red area, contribute roughly 1.5% to 2%, while the RSMQ136, which is the green area, occupy the top 2% to 3%. Is the decision tree. We as a group decide to separate every single sensor to have a proper decision tree analysis, as you can see from the slide above. Now we're moving on to the regression. The functional analysis of the linear regression graph, which is the humidity versus RSTGS2442. This graph illustrates the mathematical relationship and cross-sensitivity effects between an environmental variable, which is the relative humidity, and a sensor electrical property, which is the sensor resistance, and in this case is the RSTGS2442. So for the independent variable S, which is the x-axis, is the relative humidity, which spans from roughly 33% to 59%. Also, so the next y-axis is the sensor resistance RSTGS2442 for ranging from approximately 180,000 ohm to 340,000 ohm. The green circles, which is the data point, represent the raw data values logged from the gas system sensor data sheet that we collect on the first page. The regression line, which is the red line, is the best fit linear model derived from the dataset to capture the global trend. The statistical finding and the mathematical interpretation is negative correlation. The first one is the negative correlation. The red regression line slopes downward from left to right, indicating a negative relationship. As relative humidity increase, the electrical resistance of TGS2442 sensor tends to decrease. This happens physically because water molecules absorbing onto the metal oxide semiconductor surface increase its electrical conductivity and also reducing total resistance. The second one, of finding of the statistical and mathematical interpretation, is the goodness of fit, which is the R square equals to 0.1095. The coefficient of determination R square is approximately 11%. This indicates a very weak linear fit, meaning that humidity fluctuation alone only explain about 11% of the variance in the sensor resistance. From this regression graph, we can see that the cyclic or hysteresis loop, the data from distant snakes like horizontal loops between 40% and 54% humidity instead of following a straight path. This indicates structural lags, which is hysteresis, or cyclical testing phases over time, where resistance rise and fall independently of the immediate humidity value. And last but not least, the lower boundary baseline show a large concentration of data point aggregate horizontally at the very bottom, which is the boundary around 185,000 ohm. This shows that the sensor hit the physical saturation floor or baseline limit at various humidity level throughout the test run. Now we move to the ThinkSpot dashboard. So the first one is the master time series table. The master time series table serves as a primary data repository on the interface. It displays the raw chronological of log of every telemetry entry imported from the spreadsheet. For each discrete timestamp, the table aligns the environment variable, which is the temperature and the humidity, with the raw resistance value of gas sensor, which is the TGS 24442, MQ4 and MQ136. This comprehensive view allows operators to inspect the exact state of the entire system at any given second, establishing the baseline truth for the historical test run. The second one is the maximum temperature certificate. Because the data set is static, standard real-time dials will remain frozen on the final row of the imported file. To provide analytical value, this card utilizes ThinkSpot's mathematical data aggregation engine. Instead of displaying a single snapshot, the widget scans the entire selected time frame, identify the absolute peak temperature recorded, which is 31 degrees Celsius, and display it as the key metric. This design pattern gives viewer immediate access to the environmental extreme of the test run without requiring manual sorting of the dataset. The third one, which is the select data range controller. So the historical dataset requires precise temporal navigation. The data range controller acts as a global filter for the entire interface, overriding default real-time clock cycle. When an operator modifies the data range, step size, or active interval on this widget, it dynamically updates the query parameter for all connected tables and chart on the dashboard. This ensures that all visualization remains synchronized to the exact historical window under review. So for the fourth one, which is the Markdown information card. The system documentation is critical for interpreting static data. The Markdown card serves as a static metadata repository, which is basically defining the boundaries of the dashboard for the third-party viewer, and it states the file source, which is the gas system sensor XLs. And that lists the active hardware components and outlines the primary analytical objective, which is the examining the correlation between environmental temperature and sensor resistance. This context ensures that any analyst can immediately interpret the purpose and the limit of the display data. And the number 5 is the individual gas sensor table with the heat map threshold. So for the bottom row, there is featured 3 specialized tables dedicated to individual gas sensor, which is MQ4, MQ136, TGS24442. This table uses a custom JavaScript style function to implement conditional formatting based on the physical operating principle of metal oxide semiconductor MOS sensor, where a drop in resistor, which is measured in ohm, indicate an increase in gas concentration. which is the MQ4 table showing the high hazard red, for MQ136 table, which is moderate warning orange, and for the TGS 24442, which is safe baseline, which is in at the green.
In conclusion, this study successfully developed a data-driven framework to improve the performance of metal oxide semiconductor gas sensor for confined space monitoring. By analyzing data collected from the TGS 2442, MQ4 and MQ136 sensor, the researcher identified how temperature and humidity affect sensor performance and contribute to sensor drift. Using statistical analysis and machine learning technique, the system was able to reduce environmental interference, improve detection accuracy, and minimize false alarm. The integration of IoT technology, artificial intelligence, and real-time monitoring through ThinkSboard makes the gas sensor system more reliable and practical for industrial safety application. Overall, this project demonstrates how data analytics can significantly enhance gas detection system and help create safer working environment. That's conclude our presentation. Thank you.